Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Marco Conini. Marco is faculty at UC Louvain in Belgium. He's been doing a lot of work in the SDN space. And today he's going to be telling us about recent work on replica selection. So, over to you.
All right. Thanks very much for the introduction, Tesh. So as you mentioned, you might have known me for SDN, but today I'm going to talk about something completely different. So specifically, I want to tell you about some work that I did with the PhD student Lalit Suresh that I advise with Anja Fallman at TUB, and with Stefan Smith, who's also at TUB and T-Labs. So let me start by saying that as users of interactive web applications, certainly all of us value very much low latency. It's really good to have a snappy user experience every time we use interactive web applications. And low latency is so crucial that the point at which it degrades user experience actually directly impacts revenues as well. So increasingly, system designers at companies like Microsoft, Amazon, Google, Facebook, and so on are starting to care when they do design their systems about the long tails in the latency distribution, even at the 99 or the 99.9 percentiles. However, it's actually very challenging to deliver consistent low latency, and in particular to keep the tail of the latency distribution short. And let's see why there is actually a fundamental problem behind this. So these interactive web applications are typically structured as multi-tiered, large-scale distributed systems. What I'm showing here is an example of a small section, actually, of the architectural diagram of the Obama election campaign from 2012, where, if you recall, Obama was making extensive use of AWS services. Now, this type of architectures of loosely coupled clusters of communicating components is nowadays becoming the norm across industry. And what it means is that even serving a single end user request may involve contacting tens, if not hundreds, of servers. And for example, if you consider when you contact Facebook and you want to render a single web page, that request involves contacting the social graph server, and it involves contacting, making hundreds or thousands of data accesses and across tens or hundreds of servers. So if you have all these many components, the probability that something may go wrong increases exponentially. So even temporary latency spikes from individual nodes may ultimately dominate the end-to-end latency observed by the users. So it's actually challenging for application providers to keep the tail of the latency distribution short for these interactive services, especially as the size and the complexity of the system scales up or the overall system use increases. For example, it was found by a study that was done by your colleagues in the other side that in Microsoft Bing, over 30% of the analyzed services have 95 percentile latency, 3 times higher than the median. Okay, so that is potentially making a lot of people unhappy. And because these applications are built out of many components and they span entire clusters, it is natural that the variability of response times at the system components would inflate these end-to-end latencies and lead to high tail in the latency distribution. So at this point, you may actually be curious, but what are actually the causes of these performance fluctuations that happen? So the reality is that these performance fluctuations turn out to be the norm in many of these settings and many data centers, and can actually arise because of many reasons. So let's review a few of the causes. This is not going to be an exhaustive list. The first one certainly is resource contention. So here we have machines that are going to be shared by many different applications that are contending for shared resources like CPU cores, processor caches, memory bandwidth, network bandwidth, and so on and so forth. Or even they are contended by the same applications, different parts of the same application contending for these shared resources. In addition, we may have typically skewed access pattern because the variability here arises from the fact that the popularity of given objects are not uniformly distributed. Then we have several queuing delays because workloads of these applications typically entail some level of burstiness and therefore produce varying degree of queuing either at the network switches or system buffer or the storage layer. And finally, last but not least, we also have a plethora of background activities taking place all the time. This may include, for example, a periodic log compaction in the storage systems like Cassandra, where they want to take whatever was written to memory, compact it, and store it to disk more efficiently. Or for garbage collected languages such as Java, you have periodic garbage collection that introduce a clearly identifiable latency spike. So all these causes essentially make performance of applications less predictable. And the questions that we want to tackle in this project is, how can we enable data center applications to achieve more predictable performance? Now, let me remark here that the observation that we make is that the workflows of this application involve accessing large volumes of data. So we regard the storage layer as a component that sits on the critical path to serve the requests. Therefore, we focus for this work on low latency data stores, such as key value stores. And we hence base our study on the popular Cassandra distributed database, which is designed to store and serve larger than memory data sets. However, let me remark that the ideas and the principles that I'm going to present are more general than just their application to Cassandra. Okay, so in particular, this is what we focus on. We focus on the problem of replica selection, wherein you have a client node that has to make a choice about selecting one of multiple servers that are all replicating the same data object that can be served for a particular request. Now, there's been recent efforts that have tackled the problem of reducing tail latency. And they made use of techniques such as giving preferential resource allocations or guarantees, or duplicating or reissuing requests if, for example, the request does not return within a certain timeout, or perhaps trading off the completeness of a request for latency, or in other cases, creating performance models that will predict the stragglers in the systems. And typically, however, this type of system they want to achieve very high availability levels. And in order to achieve very high availability, they use replication. So there is essentially the ability to exploit replication at an underlying layer, which is basically sitting below all these approaches that, for example, duplicate requests. And this is where we focus in this work. So in a sense, we're also complementary to other approaches. And we exploit the redundancies that is typically built into each of the tier of the application architecture. So what we focus on is the specific replica selection algorithm. And as you might expect, this turned out to be quite challenging. In particular, there are two major challenges to this approach in the settings that we consider. The first one is that these data center applications, as I mentioned, exhibit service time variations. Okay? Their performance is not always predictable. The second problem in creating a replica selection algorithm is that we want to avoid the so-called herd behavior, wherein essentially you would have a plethora of clients focusing on a given server because they perceive that that server is the fastest at the moment. So we want to avoid this type of load imbalances. So let me discuss in detail what these challenges entail. So the first one is with respect to the service time variation. So I mentioned that all these servers in this data center settings routinely experience performance fluctuations due to multiple reasons. And in these settings, the replica selection necessarily has to adapt to the heterogeneity of this condition, okay? Which means that over time, what we may observe may actually be changing in terms of the service time that we're going to see. So in these settings, the strategy that is commonly employed in systems that are in production today is the so-called least outstanding requests strategy. So for each request, essentially, the client would select the server to which it has the least number of outstanding requests towards. And this is a very simple technique. It requires only local information because each client can make his own decision independently of any other client. However, this is not ideal for targeting the specific problem of reducing the tail latency, because many of the realistic workloads are skewed in practice, and the access patterns will change over time. And underneath, the service times are also changing. So we want something that can adapt more quickly than just least outstanding requests could. On the other hand, if we want to design a robust replica selection algorithm to be adaptive and stable, well, that turns out to be very challenging, because if we do not carefully design it, we run into this problem where multiple clients are coaxed to direct requests towards the least loaded server, and this necessarily degrades that particular server's performance, which subsequently causes then the clients to perhaps repeat the same procedure with a different server. So there is the risk essentially of synchronizing that behavior in the cluster and introducing load imbalances. So for example, I want to illustrate this with some experiments that we did using Cassandra on Amazon Web Services, where we were measuring the 99.9 percentile, which turned out to be 10 times higher than the median latency. What I'm showing here is the requests that are measured as in intervals of 100 milliseconds. And you can see that this is one given server. So every server sort of in the cluster would show you a similar behavior. Over time, you have a major trend, which is serving around 300, 350 requests every 100 milliseconds. However, you have all these data points here that make it so that if you just consider the 99.9 percentile, you have 10 times the median latency. And just to tease what's going to happen with our approach, this is the type of load balance that we are looking for, how to condition the cluster behavior. So what I want to talk now is our scheme, which is called Seefree. This is an adaptive replica selection mechanism that is robust to the service time heterogeneity, and it adapts to the varying conditions. So in designing Seefree, we have two clear and distinct goals. The first one, as I said, is to cope and quickly react to the heterogeneous and time-varying service time across all the servers. The second one is to be well-behaved. So we put specific effort in making sure that the clients performing replica selection avoid this type of herd behavior. In order to meet these two goals, we have two components that we introduce in our strategy. The first one is replica ranking, and the second one is distributed rate control. And now I want to walk you through these two parts. So let's start with replica ranking. So the idea here is actually quite simple. We want to use a minimal and approximate feedback that we get from the servers of our system to let clients rank, from their perspective, each server in the cluster according to a certain scoring function, and then pick replicas based on the score values that they obtain. So let me give you an example. Consider this system where we have essentially two servers with different service time. Okay, I use the notation mu, which is the service rate, and 1 over mu refers to the service time. And then we have 3 clients in this case, which are accepting requests. They may come in, for example, this could be the application servers of the application. This could be the storage layer, and the request may refer to the request that the user generates from the browser or some other requests that come into the system. So in this, and they may arrive in burst. So in this case, assuming a static scenario where the service times are not changing, then it's quite easy to see that there is no better solution than balancing the request across the two servers in such a way that we obtain 12 milliseconds as the maximal latency. And this gives us essentially a basic intuition, which is that if we want to target the tail latency and minimize it, then we want to minimize the product of the queue size and the service time. So the challenge here is to do this, however, in a decentralized fashion without having clients to actually coordinate with one another, while also adapting to the service time variations. And the main idea is that we use this replica ranking. That is, the clients will individually rank the servers according to a scoring function and use the score value as a proxy for the latency that they would expect. Yes?
Are you targeting disk-based or memory-based systems?
So in this context, we are targeting servers that are acting, that are providing a storage layer. So we have results for Cassandra, which is designed to serve larger than memory datasets. Okay, and we have done experiments by using both spinning head disks as well as SSDs, and we specifically target the settings where the service time for serving particular request changes for both internal or external conditions to the system design. In doing that, we have not considered workloads that just read out of RAM, out of memory. For example, in systems like Cloud RAM, where the entire data set is served straight away out of memory, they have specific system design such that the service time to respond to any particular request is in the order of microseconds rather than milliseconds. So we have not extended our study to those settings.
The point about fitting this is your service time will be a function of your queue size.
It can be affected by the queue size.
Just need deep queues.
Yes.
Do you model them, or what do you do?
So we want to avoid actually deep queues, and I'm going to get to that while discussing the second part of the approach. Yes. Was there another question there?
But if there are disks involved, then the service time will also be a function of not just the queue size, but what's in the queue.
It's also a function of the type of requests and potentially of the popularity of the objects, etc. So we do not model that one explicitly. We raise a bit the abstraction here, and we consider the fact that the server has an overall capacity that is being estimated, and we want to adapt to that. And the rationale for this is that the servers are, as I said, replica of one another, and they can be chosen as an alternative. However, what matters is fundamentally to reduce the tail latency rather than finding the best allocation of all the requests to the servers. So there is more details, certainly, that can be included in the model. Okay, so going back, my point here is that we want to do this in a decentralized fashion, avoiding the clients that the need to coordinate with one another. And the main idea then is that we have clients to rank the servers individually and then use this scoring function to determine a value that corresponds to the expected latency if I were to send the request towards that server. So now the question becomes, how do we actually compute the server scores? So intuitively, we should start by estimating the queue size and the service time, because those are the two components that we use for selecting the best server. So the idea then for us is to use some feedback from the servers so that we can estimate this value. So we assume that the server will be capable of piggyback the queue size and the service time for every response. In particular, when I send a request to the server, then the server will send back how much time is spent serving a particular request. Okay, so that does not account for the waiting time in the queue. And the queue size as recorded after the request has been serviced. And so, of course, here there is a little bit of delay. So it's a reactive system, right, that is being fed information that were precise at a particular point in time in the past. Okay, but I need to use this to actually make a guess about the condition of the system in the future. And we want to essentially maximize the likelihood that we're going to be making the best decision. So the way it works at this point is that the clients actually smoothen this signal, so they maintain exponentially weighted moving averages of the metrics that are piggybacked by the servers. And at this point, we may be tempted to simply use these estimates and compute the product of queue size and service time, Okay, but the point is that this is just delayed feedback from the servers, and it gives clients only an approximate view of what's going on in the cluster. So they don't have a precise information about the load across the servers. And so we find that this is not sufficient by itself. Particularly, this is the case because clients are not aware of the existence of other clients in the system, as well as what are the requests that are currently in flight. Okay, these are not being considered.
Question, can you just
Yes.
clarify, is it the server that's sending back the exponentially weighted moving average of its own behavior?
No.
Or the client
The
is
cli-
taking an exponentially weighted moving average of what the server has sent?
The second one, the client takes the exponentially weighted moving average of what he receives.
So why are you assuming that the client is better placed to do the smoothing than the server?
So you could be doing the smoothing at the server and send just an aggregate value that represents the conditions of the server overall. We found that by maintaining the signal at the client gets a perception of what he is actually asking the server to do, rather than getting information that is across the entire server usage. Sorry. It could be that both ways are both ways perhaps work in different settings. We found this to be sufficiently good in our settings, but I don't have like an answer as for which one would be better in which case.
Think about it from an information theoretic point of view. It ought to be better for the server to do the weighting than the client. Because the server has strictly more information about what's happening in the server.
That is correct. Ultimately, what I can say is that these are approximate measures for which all that we want to do is we want a client to produce a relative ranking of the replicas, and the settings that we consider are trying to replicate the common production settings for which replication factors are in the order of 3 or 4 replicas. So ultimately, what we're trying to do is to say, is this server better than another one for my own workload at this particular point in time? Yes, Chris.
That will make a difference is that now the different clients can actually do very different estimations of the server load, because they may receive updates in very different rates and so on. So they may see a very different clients may have a different view of the load of the servers, and that may introduce instability in the allocation of clients to servers.
So that is a good observation, and in fact, I'm going to basically cover that in just a second. So we did find fundamentally that this is still not sufficient to avoid the synchronization, and what I'm going to discuss in a second is the mechanism that we use to essentially trade off if you wish, the optimality of the decision based on the feedback that the client has versus the discounted probability of essentially hitting a bad server. Yes?
Some of these in the past with the Disconnection in the Everest project, where we also piggybacked feedback like that. And one of the things we found was that actually the servers with the worst muse end up giving you the lowest quality information because they're not sending responses back quickly. So you actually have bad information about the servers you really most want to know about. So it's not really a very stable system.
Yes, that is not stable enough. That is true. We also experienced this. So essentially,
Presumably you also have the problem that good news travels very slowly, right? If I believe some server to be horrible, I'm not going to send it any requests. Therefore, I won't get any feedback. And therefore, if it has actually on jump, I'm not going to know about it.
so there is a trick that we use here, which is exactly addressing this problem. The problem is that it would seem as though essentially if you stop using a server, you're not going to refresh any information about the behavior of that server, and you may not be interested in using it anymore. So what happens is that in several of the systems that are deployed as a storage layer, there is this concept of repair operations due to the consistency model that this distributed database use, which is not strongly consistent but eventually consistent. And therefore, with a certain probability, which is configurable, and we find in typical usages it's about 10%, a given request is actually being sent to all of the replicas rather than just a single one. And so we exploit this as a way to gather information from nodes that otherwise we would not be accessing. Okay, so now that we have discussed this problem with just using the EWMA of the feedback from the servers, so we found that this is indeed not sufficient by itself. The reason is we are not really, as a client, we're not really aware of what's going on in the system. So what we want to do is to introduce a term in our scoring function, and this term is something that we call the concurrency compensation, which is going to account for the potentially concurrent and in-flight requests to the servers. The way that we do so is that we actually come up with a simple formula that is our estimator for the queue size as at the particular server as in the future. So every time that the client is about to make the decision about which replica to pick, it will basically estimate the queue size of the server according to this formula, where he accounts for his own requests, and then he accounts for how many outstanding requests he has towards that server, as well as the number of clients in the system that we assume is an information that is available, because these are deployed applications in data centers. And ultimately also the QS term, which is the EWMA of the QS as inferred from the measurements at the server. And so the intuition here is that this design will provide a certain degree of robustness to the synchronization among the different clients, because the clients here would always account for the possibility that there are multiple clients concurrently submitting requests to the same server, and a particular client that has a so when estimating this concurrency compensation, a client that has a higher number of outstanding requests towards the server will ultimately implicitly give a higher value for the queue size estimate. Okay, and when we're going to feed in this into the scoring function, lower value means better servers. So a higher value for the queue size estimate means that this particular server may be considered, may be ranked more poorly than another one. So clients that have different workloads, okay, will actually work. They will work in a coordinated fashion towards finding out for themselves which server would be better. Yes?
Something I'm not getting.
Yes?
You're going to have at least thousands of clients and hundreds of servers, so that N is going to be order of 1,000. But 990 and the rest of them will not be talking to a given server at a given time. So that term is going to dominate, and that seems wrong.
Let me clarify what I mean by clients. So what I mean by clients is not users of the website, okay? What I mean by clients is the front end, okay?
Thousands.
So these are application servers.
Thousands.
I mean, you're not taking example of being in Amazon, right? Where you're talking with your front-end servers, you're talking tens of thousands minimum, right?
So, well, I'm not aware of the applications in which you would have literally thousands of clients, so thousands of application servers sharing the same Cassandra cluster. Probably this is not the settings that we've been considering. So
the motivating examples were being in Amazon, so if you changed to different motivating examples, tell us.
No, I'm not changing. So the motivating example is that applications are structured as multiple layers of clusters of components. So when we talk about clusters of components, we talk about tens or hundreds of servers that are communicating. I'm not aware of a system where you would actually have thousands of application servers all talking to the same Cassandra cluster. But I'm happy to be proven wrong here.
I don't know how big Cassandra scales, but I think if Bing and Amazon are your motivating examples, you have to consider key value stores that scale a lot larger.
Okay, so what I can say is that the results that we have, okay, in the results that we have done, we have scaled up the term N here to hundreds, but we have not evaluated it with thousands.
Even with hundreds, isn't that term always going to dominate? Are you keeping hundreds of requests outstanding at a given server at a given time?
The request, the way that we find is that the requests typically are in a closed loop fashion from clients. So from the point of view of the application logic, okay, when they do submit requests to Cassandra, it's a synchronous operation or a batch operation of several requests that will count as one in this case up until the server returns a response, and then the application code proceeds.
But if the offered load from the outside world changes,
yes,
or it's not what you expected,
yes. But so if the offer load from the external world changes, right? At that point, there's going to be essentially something that has to do with the scalability of the system. One thing that I was going to mention later, but I can mention it right now, is that the settings that we are targeting, okay, are high utilization settings for the underlying storage cluster, in which we do assume that we are having utilizations of 80 to 90% of the underlying cluster. So we basically consider that if extra scalability is necessary, okay, that is not necessarily our problem to adapt to. So it means that new capacity has to be provisioned into the system.
So what's the typical value for outstanding requests, if I understand it?
So, I'm sorry.
What is the typical value for outstanding requests?
So the typical value for outstanding requests from the point of view of the client, we assume that this is actually quite small because of this closed loop for submitting requests. So I would say it's in the order of 1 to 10.
And what is QS? What typical value of that?
The QS, we basically have small values here because we, as I'm going to show in the next part of the talk, we actually introduce an element of rate limiting based on an estimation of the server capacity, so that we aim at maintaining short queues at the servers.
So it will be dominated by that middle term then?
Yes. But let me make one remark that this. So we have struggled a little bit with this queue size estimate, and perhaps it's not the best way to actually term it, because indeed it's not really an accurate estimator of the queue size, but it's something that we plug into the scoring function, whose outcome is just to be able to produce a total order of the replica servers from the point of view of the client, and it's not going to be used as an actuator, say, as the rate limiter value, okay? So this is just for us to be able to say which server do we believe will provide us a faster response time. And if you do have ideas about, changing this, just come and talk to me at the end. I'll be happy to if you can share that.
The worry here is pretty much every client is going to make the decision based on how many outstanding requests do I have, because that n is going to be large. Right. So it kind of almost, I'm trying to see in real world terms, how is this different from the thing you described before, which is least outstanding requests?
Shall we see the rest of the slides?
Yeah, right, that's good.
Okay, let's come back to that. That's a very good observation. So the point here to continue is, now that we have a particular value for this Q hat S, and we know what the service time would be, should a particular client, any given client, just choose the minimum of that ratio or not? And we find that essentially, if we were to use such a scoring function, okay, it would not be very effective in the way that clients would rank the servers among each other. And to see why, consider this example where we have two servers that have different service time. One is 4 milliseconds, so it's much faster, and the other one is 20 milliseconds, meaning this is a much slower server. And from what you can see in this graph, essentially here the trade-off is that any particular client would only choose to pick the slower server, okay, if the queue size estimate for the fastest server was above 100. Okay, I recall that we would basically use this as a scoring function and pick the lower value. So this essentially causes the clients to build up and maintain long queues at the faster servers, which is actually something that we want to avoid. The reason that we want to avoid is that if the faster server was to become significantly slower, for example, due to garbage collection or some other background activities, then all the requests that are at that moment in that queue, they will suddenly experience higher waiting times. Okay, so this scheme would hamper the reactivity of our approach. And to solve this issue, what we do is we design the replica scoring function around the idea of performance proportionality. What I mean by this is that we aim to find a balance between keeping the queue lengths proportional to the service times, but also penalizing excessive queuing to discount the inability to react quickly to the service time variations in the future. So in practice, what we do is that we build a scoring function that penalizes the longer queues by adopting a non-decreasing convex function of the queue size estimate, which in our case is the cube of the queue size estimate. And so if you consider again the previous example, this means that with this scoring function, Seefree will treat the above two servers as being equal in score if the queue size estimate of the server or the fastest server contains around 35 requests instead of 20. And the reason here that we choose the cube in the function is because for us it presents a good trade-off between clients preferring faster server and providing enough robustness to this time-varying service times.
It seems that you have put a lot of effort in avoiding this problem synchronization. And another approach would be to have the clients either pick a small set of random subset, a small subset of servers at random and then pick the best one, or take the top k and then pick a random from the top k. And these seem to be better kind of heuristics to avoid this problem. Have you considered and have you compared?
Yeah, so that is a very good observation. So that is the power of two by Mitzenbacher. So we have considered that. However, fundamentally, the motivating case for that work is that you have, hundreds of or thousands of replica servers available, and you basically don't want to. Sorry.
You also have hundreds of thousands of replica.
Yes. But the replication factors that we consider is in the order of 3 or 4, meaning that you can only choose among 4. So the cost of actually ranking all the 4 choices relative, to the case of K is much smaller. So we don't need to amortize that cost.
Can you give me intuition for why you want a cubic? Why are you not just measuring the queue size in milliseconds rather than in requests, for example?
So the queue size. Sorry, what does it mean to measure the queue size in milliseconds? Like the amount of queuing time?
You have a reasonable argument, right? Which is that if you let the queue size become too long on a fast server, then it's hard to respond to it. Well, I guess that's just dividing through by the rate at which it's servicing requests is equivalent to measuring it. Why cubic? Why not square or?
Yes, so it is a bit of a trade-off there. Okay, so we have not fully explored the space of that value. We have done essentially simulation experiments with basically taking the quadratic or cubic or even raising it to the 4. And again, this is essentially a trade-off that needs to be explored. We are now conducting a more analytical study to understand this, but it's very hard to find. I mean, we don't believe that there can be a closed form expression to this to be able to derive what's the optimal exponent to be put in there given a particular workload.
Well, why does it make sense at all? I mean, one of the ways to think about this is why does the RTT between the client and the server not figure in this, right? Because there's a certain delay in the server reporting effectively what the behavior is at the server, right? So why does that not figure in the adaptiveness?
So it will. So what I suggest is that I move quickly to the next part, okay? Because I noticed that we're quickly running out of time, but I'm available to discuss this in more details afterwards. All right. So this is the second part, which is indeed related to taking into account more information, and that is not an explicit feedback from the server either. So this is about doing distributed rate control, where the high-level idea is that every client will rate limit the request destined to each server based on an estimation of that server capacity, and it will adapt the rate in a fully distributed manner. Okay, so let me describe. Well, I think we had a lot of discussion why we need this, okay? But the main point here is that we want to keep queue time short and avoid especially overwhelming a particular given server if clients are not aware of each other's decisions. So what we end up doing is that to account for the server's performance fluctuations, the clients need to adapt the estimation of the server capacity and adjust their sending rate towards a particular server. As a design choice and inspired by the cubic TCP congestion control scheme, we use a decentralized rate adaptation algorithm for clients to estimate and adapt the rates across the servers based on a cubic function again. So essentially here the clients would track the receive rate as perceived when talking to a given server. So this is just passive information that is being measured at the client. And we check whether basically the number of responses being received from a server in a given time interval delta milliseconds. And then we use this information to adjust the rate limiter with the QB function, which is a function of a delta t. And this is how long it has been since the last rate decrease event. So the reason that we pick this QB growth function is that it has the desirable property of having a saddle region here in the middle. So fundamentally, what happens is that the client would first, in this lower rate region, try to ramp up its sending rate towards the server. And then when it gets around the saddle region, okay, it will not be as aggressive in growing the rate. And if it has spent enough time in the saddle region, then it will optimistically probe again for additional capacity at that particular server. If the receiving rate isn't increasing further, right, then we have a multiplicative decrease as in TCP. So the way that we combine this by putting everything together, fundamentally you have to envision that Seefree is a client-side library with a few modifications to the servers, and it contains a backlog queue here, a replica selection component, and then rate limiters towards each server. So it gets the feedback, and then it will sort the clients. It will sort the replica servers by the ranking function. Every time that there is a request, it will pick the replica that is ranked the best, for which the rate limit that is still within the rate limit, and then send the request to that server. And if we are in the conditions that all the servers have exceeded the rate limiter, then it will retain the request in the backlog queue up until the first of the replicas becomes available. Yes?
So a few years ago, the VMware guys had done some work that is called Pala, where they were trying to fairly share storage services, and they adapted TCP fast to do this capacity estimation. And what they had observed was that a single client's estimate is actually not very noisy, and they had to do coordination between clients. And I guess, so some work we did here, that's why we actually moved to solving this problem using a centralized controller. Mm-hmm. And I'm wondering what's changed here that led to solve this problem in a distributed fashion.
I don't think I have an answer to that.
And you should look at the paper because they had a very
so we are aware, we are aware of the work and the fact that they were using the fast TCP inspired mechanism. So on my feet, I don't know what would have changed in the settings. So there is one difference, of course, in the settings, which is that what we're actually trying to do is not to share the storage bandwidth of the servers, but in a proportional fashion. But we we are actually trying to not overwhelm individual servers based on the estimate that we have. So I guess one difference that stands out for me here is that there is no notion of proportionality across the different servers, between the different clients of the service. And that aspect may not matter. So all that matters is that we aim to keep queuing delays short at the servers. But we can discuss this more offline. Yes?
This is just read requests, or is it reads and writes?
So this is a good observation. So far, I did not mention, but we do target read operations. The reason for that is that the write operations typically do involve more than one write, okay, into the service layer. So at that point, you're going to have to write into all the replicas anyway. So there isn't much that you can choose. But it's a good observation, and we want to study essentially the issue of assuming a different consistency model than just write n and read 1 from n, and to see whether this could also help.
You assume that all reads are the same size?
So we have done experiments in which we have varied the field size. I'm going to get to that during the experiment. But we do have experiments, and the bottom line is that we still observe that our scheme is able to beat the baseline, which is the dynamic snitching algorithm within Cassandra. Okay, so speaking of Cassandra, so we implemented and tested Seefree in Cassandra, just to make sure that everybody is on the same page. Cassandra is a distributed database, okay, and it fundamentally resembles the way that Cord introduced the concept of assigning different portion of the token space or the key space and distributing across on the ring. And so you have replication factors typically of 1, 2, and 3, and you may, as a simple example, follow just the ring. It's not the only policy. There's different policies. So the way that Cassandra works internally is that any client can contact any server for any request, and then if that's that server that is contacted acts as the so-called coordinator, meaning that it can see that the request completes even though he is not the replica server for that particular data item. So the way that it works is that it is aware of the token space, and then it will make its own replica selection. The way that this is done within Cassandra is to inform the coordinator node as for which replica to pick. It will use the module called dynamic snitching. Now, the way that dynamic snitching works is that it will constantly and periodically, every 100 milliseconds, acquire information from all the nodes of the ring as for what is their value of I/O weight that were spent during the past 100 milliseconds inside that server. And this is essentially a proxy of how loaded that node is in terms of I/O activity. And then the coordinator also tracks his own network latency to all the other nodes in the cluster. So at the end, basically, the coordinator can just ask the snitch who is the best replica and make a decision. So what we did is, to implement Seefree, we replaced the dynamic snitching component. So we essentially implemented Seefree as a client library within Cassandra itself, rather than outside. This also goes back perhaps to why we see such great results, is because also with the experiments that we conducted have in the order of the experiments on Amazon have in the order of tens of nodes of the Cassandra cluster. So we have not tried yet with hundreds of nodes, but it is on the roadmap. Specifically, it's in the roadmap to adopt the STNX Cassandra client to implement the Seefree logic inside the clients of Cassandra rather than inside the coordinator. And yeah, it wasn't easy to write this code, but Lalit did a very excellent job, and it turns out there's also not that many lines of code. So in order to evaluate our approach, we conducted experiments of the implementation, both on Amazon EC2 as well as a control testbed. And then we built a discrete event simulator But I'm now going to present the results for this latter two. So I'm going to today focus on the Amazon experiments, where we set up a cluster with 15 nodes, and we used the YCSB to generate workloads. Okay, specifically here we created 3 different workloads where the requests for the keys were distributed according to a Zipfian access pattern rather than a uniform. And then we had read heavy, which is 95% reads, 5% writes, update heavy, that is 50-50, and then read only, which is essentially 100% read operations. And we compared this, we compared Seefree against the dynamic snitching approach. Now, what we found is that regardless of the workload that we use, Seefree improves the latency across all the considered metrics, namely the mean, the median, the 99, the 99.9 percentile latencies. And we found specifically that at the 99.9 percentile, we would have 2x to 3x improved latencies when compared to dynamic snitching. Furthermore, we saw that by controlling actually the waiting times across the replica, Seefree makes better use of the available system capacity, okay, resulting in an increased throughput across the considered workloads. This is because the load conditioning in the cluster is better. And so we found that even the throughput is increased between 26 to 43% across the considered workloads. We also verified whether Seefree fulfills the design objective of essentially avoiding the load pathologies. So as I said, we do use a Zipfian distributed key access pattern. And what we focus here is on the load over, so we observe the load over time for the node that has served the highest number of reads across each run of the experiments. So here, every experiment was repeated 5 to 10 times. And we focus on the most utilized node. And so what you can see here is that fundamentally, as a CDF, you can see that the most utilized node would actually end up serving fewer read requests because the entire load is more fairly distributed, well, is more balanced across the entire cluster than what dynamic snitching would end up doing. And this is also a contributing factor as for why we find that we overall we increase the system throughput as well. And as a further confirmation of this, if you remember, I showed you earlier the load as witness at a particular node where we were using dynamic snitching. And this is instead what we find with Cassandra. We have an improved load conditioning where the load is more evenly distributed in the cluster. Yes?
Quick question on that. So am I reading this right? In the C3 case, the request per second is actually lower, so the system throughput is lower, but in a more controlled
the per node system throughput is lower. That is correct. But the overall cluster throughput is higher. And one contributing factor to that is indeed that you have lower per node throughput for the most highly utilized node in the cluster. So it means that we have.
Oh, I see.
This is just the most utilized. Yes.
Right.
You get a chance to compare this a little bit to just sending the requests to all replicas, like Javine has been talking a bit about that. And simply because reads, if you're just considering reads, they're really cheap, right, to send over the network. It's just a little bit of a header.
Yep.
So sending them to all replicas, waiting for the first one to reply, and then canceling the rest is one of the things he was proposing, and I think has implemented the Google, right? Have you,
right.
Is that a fair comparison?
It's not. I think it's not a totally fair comparison, but we did run this experiment. So let me remark that in Cassandra there isn't a readily available implementation of request cancellation. So what you were talking about was what's called request reissue. So you send a request, you wait for a certain timeout that is typically set to some high percentile of the distribution. And then if the timeout expires, you send the request to another replica, okay? And at that point, what you can do is when you get the request back from one of the server, the earliest one, you can cancel the other one, or in a more clever version of this, which is what I believe Google implements, the servers would talk to each other to actually cancel the request at the other server. So this is not currently implemented in Cassandra. However, Cassandra does implement the ability to do the request ratios, and we did experiment with that version of request ratios that is implemented in Cassandra. Now, we don't know whether we stumble on some kind of bug that affects that code path in Cassandra, but what we found was that actually the overall performance of the cluster was degraded and was even worse than dynamic snitching.
Because there might be bugs in Cassandra, but some sort of
we're working on the simulations.
Okay.
Yeah. So I think the last experiment I want to show you is reacting essentially to dynamic workload changes, in which here we have, as we were discussing before, potentially more workload being brought to the system. So here we were starting with 80 ready heavy workload generators, so 80 instances of YCSB operating in this closed loop fashion. And at about 640 seconds into the experiment, we brought in 40 update heavy generators. And then we observed again the latency profile with and without Seefree. And this is what we were observing. So in contrast to the dynamic snitching, which is here on the right, the Seefree's latency profile degrades more gracefully after this 640 seconds, and we have a lack of these synchronized spikes that instead are far more visible in the case of the dynamic snitching. So we also had run several other experiments in AWS, including higher system load, skewed record sizes, and using SSDs instead of spinning disk. And overall, we always found that at least there was a 3x improvement in the there was about 99.9 percentile latency. And also with SSDs, there is a further improvement to the throughput thanks to much faster disks. So in summary, today I presented Seefree that combines careful replica ranking and distributed rate control to reduce the tail, mean, and median latencies in cloud data stores and improve the load conditioning and throughput. So this is 11, so I think I did my job okay. Thank you very much for your question and attention and all the feedback. Thanks.